Hello, everybody. Thank you for joining us for our live stream today. My name is Grace Wolson, and I'm on the student programs team here at MathWorks.
And I'm Ryan Weinstein, and I am a content developer in the Training Services Department here at MathWorks.
And today, we're going to be talking about deep learning with images. We're going to start by going over some pre-processing and preparation steps that you can take with your images and talk about some tools that we have available in MATLAB. And then we'll go into a full example of importing and pre-processing some image data, using it to create and train a deep neural network, and then using that network to make predictions on new data. Now, for this example, we'll actually be using data that's from a data science competition that is completely online and open to everybody, called the BioMassters. We're showing that up on the screen right now. And so if this kind of work is interesting to you, I highly recommend checking it out by going to this top link, the Learn More and Register link. And this will also be put in the chat. If you have any questions at all throughout our live stream, please feel free to put them in the chat. We have some people monitoring, and we'll try to answer questions as they come up. And with that, Ryan, would you like to get us started?
Yeah, thank you for the beautiful introduction. And the links up on the screen will be back up at the end, so if you don't catch them now but you are interested, you'll have another chance to go check them out. But yeah, with that being said, like Grace said, I'll start by going through some basic image pre-processing workflows that we can do for deep learning applications. And so I'll go straight over into the image labeler app. So MATLAB has lots of different apps that you can use for lots of different things. They're basically just really nice UIs so that you don't have to write a bunch of code. You can just do things pretty easily. And so this is an app that's used a lot for pre-processing images for deep learning workflows. So that's what we'll be going over today. So we'll start with an example. So I'll go over and import from a file an image. We have this example image of boats. So we'll use this one for today. And it'll load in. And so we've got this picture of boats. We'll start with this workflow called object detection. And so basically, this will be used to train a model to detect objects and images. And obviously here, we're going to be detecting boats. So what this app can give you at the end of the day is ground truth data. Ground truth data is data that you can use to help train a network to detect objects or other sorts of things, in this case, boats. So to start, we have to add labels. That's the image labeler app. That's kind of what it does. And so we'll go add a label. We have to give it a name. So let's start with sailboats. We can obviously see there's some sailboats in the image. We want to label them so that our network can recognize them.
Simple. I like it.
Yes. We've got a few different options here. So these are different types of labels. So rectangles, lines, pixels, polygons, and projected cuboids. We'll stick with rectangles here. It's pretty simple. We can just draw a rectangle around a boat, label it. We'll keep it simple. You can also give it a color. We can leave the automatic one. That's just how the label will appear on the image. We can also have it belong to a group. So we can create a group called boats. Since there are multiple kinds of boats here, this will just help us keep our labels a little more organized. And so now we can see over here, we've got the boats group, and we've got the sailboat label. To actually label our sailboats, it's really easy. We just come over here. We can see we have this like crosshairs, and we can just draw a rectangle and label a sailboat. We can do that for all of the sailboats in the image, and we've labeled them as sailboats.
Look at that.
Pretty easy so far. We see this other boat in the background here. That is not a sailboat, so let's create a new label. We can call this one tanker, and this will help us to label the other boat. We can see it kind of saves what we did last time, so it automatically will put it in the boats group unless we tell it otherwise. We do want it to be there. So now we've got the tanker label. We can see it's already selected over here, so we can draw our label here, and now we've labeled that as a tanker. So now we've labeled all different kinds of boats, and this is great. This could be used right now for an object detection network to be able to detect sailboats and tankers. But let's say we want to do a little more. Maybe we want to also be able to identify like how many sails each boat has. We can use something called a sublabel to do that. So if we select a label and then add a sublabel, we can call it sails, and it'll belong to whatever label we had selected when we created it. So under the sailboat label, we can now see a sails sublabel. We can draw the label the same way. So we just have to select sailboat. Oh, actually, my bad. Select sails, and then we come in and, deselect that. We should be able to just draw the sail. OK, let's do it on.
Here, do you want to start over real quick?
Yeah.
Of course, it only happens when we're live.
Yes. Not sure why it doesn't want to let me draw that, but I should be able to go in and just draw a label here. Weird. Anyway, this theoretically should work.
Here, do you want to delete that sublabel and create a new one?
Yeah, let me delete the sublabel and just create it again.
Great.
And hopefully it works this time. So we'll call it sales. And yeah, we can just draw it. So we can label these as sales. And so now we label the sales. We could do that for all the sailboats, but it's just an example. We can just leave it at 1 for now. So this is pretty good. We've got a sailboat, we've got sales. We can also add other things called attributes. And so that's something that right now we've just labeled objects that we can see in the image, but we can also label things that maybe we can't see in the image, but we still want our network to be able to detect. So for example, we can add an attribute to sales and tell us whether the sale is raised. So we can call this like is raised. We can't see that necessarily from the image. Like if the sale wasn't raised, we couldn't just draw like an empty rectangle to label that, but we can use this. Oh, so there's different types of sublabels or of attributes. There's a list, which means you can add your own specific items. This one we're going to do logical because it's just raised or it's not. So it's true or false.
Makes sense.
So we can create that attribute, and it should show up in the attributes and sublabels panel. It is not.
Let's try it again.
We'll try creating that again. Call it is raised. It's logical. Okay, so it does exist, but it's not showing up in the attributes and sublabels panel. That is odd. Anyway, not sure why that's happening. I don't want to waste your time watching me try to figure it out. But basically, normally it would show up here, and you could just select a value, either true or false, to label whether these sales are raised or not. Oh, I see what happened. Anyway, it's OK. That's what would happen. And then the last thing to go over here is there's also something called scene labels. And so if we want to classify each image, we can label it as, whatever we want. So for this example, let's say we had a whole data set of different types of images of boats. One thing we want to differentiate is like daytime or nighttime, because that could definitely change the way that the boats look. So we can add a scene label, and we can call it daytime. And once we create that, it'll show up here. And we can either apply it to the image or remove it from the image. So this image is daytime, so we can apply it. We see a little check mark, and now we've told our ground truth data that this image, it's daytime, and so it would be able to classify that.
Ryan, there's a lot of information stored on this image now, but you mentioned that we can use it to train object detectors or classification networks. How do I get this out of the image labeler, and how can I use it?
That is a great question. I'm glad you asked. So yeah, we have this image. It's got all the information we want it to have, but how do we actually use it to train a network? There is this export button over here all the way on the right of the tool strip, and we can export to the workspace as ground truth data. So we can call it ground truth boats. You hit OK. It'll take a second. And we can go over to MATLAB and confirm we do have this object in our workspace called gtruthboats, and the data type is a 1x1 ground truth object. So this is a data type that can be used directly just to train different types of networks. So in this example, we could use this to train an object detection network.
Very nice.
And so that's kind of beginning to end the pre-processing workflow there. Pretty cool, pretty easy to use, but there's actually a lot more we can do in this app outside of just object detection workflows. So let's do one more example. So we'll start a new session. It's going to ask if we want to save this session. I'm not going to, because this is just an example, but typically you'd probably want to save the session. That way you could always come back. You could edit labels. You could add new labels. You could add more images to your data set. It's always good to have it saved just in case you want to make any changes. But again, for now, just an example, so we won't. So let's start the same way we did before. Import a new image. We'll use a different one this time, switch it up a little bit. And this one is of a highway. So there's some cars on the highway. This time, instead of doing an object detection workflow, we'll do a semantic segmentation workflow. The difference here is last time we just labeled some objects and drew a rectangle, said this is an object in an image, we want to detect it. Semantic segmentation is a little different, is that it works on the pixel level. So we're going to actually label every pixel in this image.
So it's kind of like classifying each pixel?
Yes, exactly. Seems tedious, right? There's a lot of pixels in this image, but it's actually not. The app makes it really easy. So again, we're going to start the same way as we did last time. We're going to add some labels. So we'll add labels for different things we see here. So we can add one for the sky. But instead of a rectangle, we're going to use a pixel label. Obviously, if we're labeling each pixel, this is the type we want to choose. And so let's create a few labels for things we see here. So we see the sky. We can see the road.
We got some cars.
Yep, cars. And we could get as specific as we want here. We could label every little thing. Since this is just an example, we'll just add a few things. So we can add like trees. And we can add like, let's call it structures. We've got like the bridge, the barriers, things like that.
Right, it looks like we have a question in chat. How is automatic differentiation used in MATLAB?
That is a great question. Off the top of my head, I don't have a great answer, but our documentation is really comprehensive, and I think a Google search would probably help to answer that question in our documentation. We do have people monitoring the chat, and so they can kind of take a look in our documentation for that. But yeah, great question, and definitely keep them coming. We want to make sure we're answering anything you guys have to ask. But yeah, so anyway, continuing with this workflow, so we've got all our labels. Now we have to actually label them. So we can start with the sky. Like I said, we're not going to label every pixel individually. That would take forever. That's not feasible. Up here, we can see we have all these different options of ways that we can label pixels. For the sky, it's a pretty big entity. Flood fill seems like it might make sense. Just judging by the logo and the name, seems like probably it's going to flood an area with labels. That's what we want. So if we just select any pixel in the sky, it labels the whole sky pretty accurately. How this works is we select any pixel in the image, and it will automatically label any adjacent pixels with similar values the same way that you labeled your original one. And then once it starts hitting like the trees here, and they're obviously different from the pixels representing the sky, it knows to stop. So that's pretty cool. We've got a little sky here under the bridge too. So let's label that. It did get a little bit of the truck because the colors are similar. We can go back and fix that later, but this is kind of why flood fill is not always perfect. But it's pretty nice for things like the sky that are really distinct from the rest of the image.
And with this color, honestly, you made it look like the weather is much nicer than it is.
Yeah, yeah. That's the beauty of being able to choose colors for your labels is, you can kind of make it look however you want. And this definitely feels like the sky, so it's a good color choice. Yeah, so the road is a little similar to the sky, right? It's kind of mostly the same color. We can try using flood fill for that too. So let's click on the road. It does a pretty good job. It gets a little bit of the barrier here. It doesn't get the stripes because those are a different color, but it does a decent job. So let's see.
Don't forget to change the label.
Oh, yeah, labeled that as sky. Good call, Grace. Change the label, and then we can try. And it, gets a decent chunk of the road. Let's try it over here. Got a lot of trees that time. So flood fill is not perfect. It's good for things like the sky that are really distinct. The road isn't quite distinct enough. So let's see other options we have. We can undo that. Right next to flood fill, we can see superpixel. If we click on that, we can see it kind of divides the image into a bunch of regions, and we can select those to label. These are pretty big, and so they're not perfectly accurate, but we have this thing called grid count, and we can move this slider around to have less or more regions to choose from. The more regions, the more accurately you can label, but also the more tedious it's going to be. And so if you want to get really accurate, you could go really high grid count, select everything you want. I don't want to waste your time watching me do that, so we're going to do some bigger regions. And so we could just select all of these that are the road, label them as road. I'm not going to be too careful about getting all of them, but obviously in your own workflow, you'd want to make sure you're labeling the road accurately. And so that's how superpixel works. It might work pretty well for cars too, especially if we make it a little bit more accurate. We can kind of fill these in and label the cars this way as well. You can see it kind of does a pretty good job of breaking the cars up from the rest of the image. And so that's kind of a decent labeling of cars. Again, we could be more accurate if we wanted to spend more time on this, but just trying to show you how this all works. Trees, this probably could also work, but there's a lot of area on this image that's trees, and that's going to be a lot of clicking. So let's see what other options we have. We do have this polygon section that we haven't looked at all. So Smart Polygon is going to work really well for trees, actually. And what this is you can draw a polygon around your region of interest that you want to label. Make sure you get your whole region in there. You can leave extra space outside of it. And so we're going to capture this area of trees, and then once you connect the original vertex, it'll label it. It does a pretty good job. It misses this little top part, and it does get a little bit of this car, but pretty accurate, hence the name Smart Polygon. It's pretty smart. It can kind of tell what we're trying to label. So we can do the same thing for these trees over here. And similarly, it does a really good job there. Actually doesn't even get any of the barrier, gets a little bit of the bridge, but does a really good job, and it's a lot easier than going and clicking all the little regions from the super pixel option.
Especially because with trees, there's so many different colors and textures. I feel like it's really cool that this worked out so well.
Yeah, so that's definitely a really nice tool. And then for structures, they're all pretty simple. They're just kind of rectangles. We can just use the regular polygon tool, and so this, instead of having to kind of infer what you're trying to label like the Smart Polygon does, this just fills in exactly what you draw. And so like the bridge is a pretty simple shape, so we can just trace it. If it's something easily traceable, this will work really well. And so now we've labeled that as a structure, and we can do that for the barriers on the road as well. And you might be noticing some of these pixels were already labeled as other things. We're overwriting those labels. So what happens if you label a pixel incorrectly and then try to relabel it is it just overwrites the original label. So it's really easy, if you label something incorrectly, to just go back and fix it. And yeah, so now we have obviously not a perfectly labeled image, but given more time and more, I guess just more time to do this, we could have a really nicely segmented image and use this for a semantic segmentation workflow.
Awesome.
This is still kind of just scratching the surface of what we can do with this app, but we want to make sure we can get to different stuff and give you kind of a breadth of options as to what you can do when it comes to deep learning with images. So that's kind of all we'll do with this app. Same way we did last time, we can export this to the workspace. Anything we create in this app, we can export as ground truth data. So we can call this ground truth highway. We can verify again that it is in our workspace. We have both of our ground truth objects, and we could use them to train different types of networks. One more thing I want to mention about this app that we're not going to have time to go into today is this automate labeling option in the tool strip. If we click select algorithm, there's a few built-in algorithms. There's also an option to add algorithms, so you can create a custom one. And what this does is, let's say you have a huge data set of images. You don't want to go through and label them all yourself. You can kind of label one and then automate labeling the rest of the images. So that's really cool and really useful. Like I said, we don't really have time to demo that today, but we will put a link in the chat to a documentation page if you're interested in being able to go and try that out yourself and follow along with some steps.
Awesome.
And yeah, so I just mentioned, right, that both of these examples are only with one image, and really when you're doing deep learning with images, you're going to have probably a bigger data set than that. One thing you might be wondering is, how are you going to store a huge data set of images in memory? Isn't that going to be annoying? Maybe you might not even have space in memory. And so that brings me to one other thing I want to share before I hand it over to Grace, which is something called an image data store. So I have an example of how those work, but essentially an image data store is an object that will point to a folder that can be stored in the cloud. It can be stored in memory, really anywhere, and only load in a certain amount of images at a time. By default, it'll load in one at a time, work with it, load in the next one. And so you can work with huge data sets without having to actually load them all into memory. This is really nice for deep learning workflows with images.
I use data stores all the time.
Yeah, they're huge. And Grace will actually be using one in the workflow that she's going to show us in a couple minutes. So we'll see it in action. But this is just kind of to introduce the concept and how it works. And so if we go into MATLAB, I already have this example food image data set loaded. If we expand it, we can see all these subfolders that are different types of food. And so this is what it looks like, what we're going to be working with. Go into the live editor, and we can see this data set has 978 photographs of food divided into 9 classes, which are the subfolders that we saw, and it's 77 megabytes in size. And so we can run this line of code. And what this did is create an image data store. So there's a function called image data store. We pass in a few arguments. So this is like what we're calling our data store. We're saying the label source is the folder names. So we're just naming our labels the same names as the folders that we saw. And we can confirm that this worked by going into MATLAB and we see this food IMDS. It's an image data store object. So we did successfully just create it. So let's take a look at what that actually did. So if we run this section, we can see some information about the data store. So 978 observations, that matches up with what we said. There's 978 pictures in the data set. We can also see how many observations per class. So 26 pictures of Caesar salad, 181 of French fries, etc.
Hamburgers are popular.
Yeah, hamburgers are second most popular. Pizza actually beat them out. But anyway, yeah, so we've got some information about our data that we can get from the data store. We can also visualize this as a histogram and see which foods there are a lot of pictures of, which foods there aren't quite as many. And we can explore it a little more even by printing out some pictures. And so we see we chose 8 pictures of different types of food that fit into those categories. So we're making sure we've got the right data. The data store has all the same images that we had in our folders. We can also do the same thing, but add kind of a drop-down option to choose only to view sushi. And we could choose any of the different types of food. And now we're seeing, these images are all classified as sushi, and they're all pictures of sushi. One other cool thing about image data stores is that you can also create something called an augmented image data store. And this is the same thing, except that it'll apply like random transformations to the images. Another type of pre-processing images for deep learning workflows is doing like rotations, changing scaling, things like that. And that kind of just makes your model a little more robust, that if pictures are weirdly rotated, weirdly scaled, it'll be able to still kind of recognize or label the types of food. And so we can define an augmenter, and what this is going to do is apply a random rotation to each image between -90 and 90 degrees, and random scaling between 1 and 2 times the original size. So we can run this, and then create an augmented image data store. And that's, same thing. It'll point to our data. We don't have to load it into memory. It has all the same nice features, but it also applies these random augmentations just to make our model a little more robust. And we can check and make sure it has still 978 observations, so we didn't lose any data along the way. Now to see how this works a little better, we can run this section, and it'll take a second. So basically we're shuffling the data, we're reading out a subset of images, then we're resetting it and reading out the same subset of images and displaying them. And we can see these are all the same pictures, but they're rotated differently and they're scaled differently. So like this pizza, it's the same as this pizza, but it's been transformed. Just goes to show, this type of data store is really useful in kind of helping make our model more robust and protecting against, these random transformations and stuff.
Got it. So like if we were training a classification model, it would be able to take pictures of pizza regardless of what angle that picture was taken.
Yeah, exactly.
Got it.
So yeah, it's pretty cool, and that's also a really useful functionality. And yeah, so I think this is a good lead-in to the workflow that Grace is going to show us. She's also going to be using an image data store. So yeah, I will now pass it over to Grace, and we can go through kind of start to finish a whole workflow of actually using this to train a model and, go through the whole workflow. So
awesome. Thanks, Ryan. So like I said earlier, the data set that we'll be using for this example portion of our live stream comes from a data science competition called the BioMassters. So if you are interested in participating, this is a great place to start. We're going to go through, importing images, using images to train a network, and then using that network to make predictions on new data. So the first step in any data science workflow is understanding your data. So let's get into MATLAB. All right, sorry, give me 1 second. Technical difficulties.
Want to make sure we're showing the right thing before we jump in.
Okay, sorry, folks. It's always bound to happen when we're live.
Always, but that's just part of it. But in the meantime, yeah, I will just add on to what Grace is saying and encourage you to, if this is interesting to you, definitely give the competition a shot. It's a pretty cool workflow. You'll see kind of an example of what it's going to look like in a second. But yeah.
Okay.
We also have a question from the chat, so we can answer that while we get this figured out. So the question is, if the data is numeric, is there a similar function for performing augmented function? Let me quickly reread that.
Sorry. Okay.
Looks like, all right, we're back up
We're
and
back.
running.
I'm happy to answer that question real quick, though,
Yeah,
if you
go
don't
for
mind,
it.
Ryan.
Yeah.
So our focus for today is on images, but there are ways to augment different kinds of data. You would use a different kind of data store for numeric data. I'm trying to think off the top of my head. But in terms of numeric data, you don't necessarily want to augment it, but you might want to do some normalization, which is something that we'll touch on a little bit in here. But augmentation is something that's more important in this image workflow because the quality and angle of images can vary so greatly depending on who's taking it, where it's taken. So it's a little more common in image workflows.
Yeah.
All right. Sorry for the technical difficulties, folks, but now we're ready to jump into our exercise. The first step in any data science workflow is understanding the data that you're given. So I'm going to just try and paint a picture for you for us to get started. So imagine that you have a square patch of land, and then we have two satellites as well that I will call satellite 1 and satellite 2. Every month, these satellites each produce one image for that patch of land over the course of a year. So at the end of that 12 months, we have 12 images from each satellite, so 24 total images for a patch of land. And then it does that for thousands of patches of land, and that is our input data set. And so these patches of land are labeled with a chip ID. That's what I'm referring to in this live script here, just so that you can keep track of which patch of land that data is associated to. And we can visualize that here. If I run this section, I pick just a random chip ID, and then I find all of the files in our input folder that correspond to that chip ID. And you can see we have S1 for satellite 1, or Sentinel-1, which is the name of the satellite. And then we have 0 through 11. So that's our 12 satellite images from S1. And then S2, which is Sentinel-2 or satellite 2, we have 0 through 11 as well. So that's our 12 satellite 2 images for a total of 24. Awesome. And then our output data looks at the same exact patches of land and says, okay, it's images. So for each pixel of this patch of land, how much above ground biomass is present in tons? And so that image is a measure of above ground biomass broken down by pixel. Awesome. And so this is another way that I visualize the data. This on the right here is what that output image would look like. And for the satellite imagery, a lot of images that you see, a lot of the images that Ryan showed were capturing the red, green, blue values, so you could just see like the colors. But these satellites measured different values. So satellite 1 is this one up here. It has 4 measurements of polarization. So satellite 1 has 4 layers. Satellite 2 has 11 measurements, and these measure a variety of things, including red, green, blue values, but also things like near infrared, vegetation red edge, and more. Again, if you want to learn more specific details about the data set, I recommend checking out the competition because they have a whole bunch of information. But at a high level, that's what we'll be working with today. So now that we get what our data set is, we know what it's doing, our goal is to create a neural network that can take this input satellite imagery and then predict the above ground biomass per pixel of that patch of land. So this on the left here is our inputs, and this on the right is our outputs. And so first we'll want to import and pre-process our data. Give me 1 second.
So I can see, kind of looking ahead, we're using a data store here. I see that image data store function. I'm just wondering, you said there's 24 satellite images,
That's
right,
correct.
for each plot of land. How are we going to read those all in at the same time? Like image data stores, right, they read in kind of one at a time. So how does that work?
That is a fantastic question. So another feature of image data stores is the ability to define a custom read function. And so that lets you choose how you want to read in your data set. And so I define this read training satellite data right here. And what that does, I've included this as a helper function in a separate file, but what that does is it basically reads in the chip ID that we're going to be working with, and then it takes all of the satellite imagery that is associated with that chip ID, and it orders it in temporal. So it's from month 0 to month 11. So we have satellite 1, month 0 to month 11, satellite 2, month 0 to month 11. And then it handles missing data. In any kind of data science workflow, you're going to have to decide how you want to handle your missing data. Since this is just our first model, it's just something we wanted to begin with, I chose to omit any images that contain missing data. And then with the images that we still had, I found the average value of each pixel for each layer. So satellite 1, I said earlier, has 4 layers. So for satellite 1, layer 1, I found the average of all layer 1s that we have. And I do the same for every other layer in satellite 1, and then every layer in satellite 2. And so what this produces is a single satellite 1 image that represents an average measurement for the year, and then a single satellite 2 image that represents average measurements for the year. Then I combine S1 and S2, the averages along the third dimension. So this ends up creating a single image with 15 layers, because all 15 of these measurements are distinct. And lastly, I rescale the values of each band to be between 0 and 1. Each of these measurements might have a different scale. Some of them might go from 0 to 1. Some of them might go to 0 to 500. So, what's a high number in one band might not seem like a high number in another band. And the best way to tell a network how to interpret those measurements is to rescale them to all be between the same value. And this is something that might also apply to just standard numeric workflows. So that makes it faster to train our models, and it makes the models understand the data a little bit better. And that's our data store. And you'll also see that I use this split each label function here. That splits our data store in between training, validation, and testing data. I've chosen to use 95% of the data for training, just because I wanted to give the model as much information as possible, but these are numbers that you can play around with, and you should when you're creating your own model. So I have the input data store with all of our input images, and then I split it up. And then I do the same for output images, but since we're just reading one in, I don't make any changes or do a custom read function. I just read in the above ground biomass images, and then I split that the same way between training, validation, and testing data. Lastly, I combine them, and so you'll see it's data store train, validate, and test. And what this does is when we're using these data stores, it allows us to read our input and output at the same time, which will make it a lot easier to use these for training and testing later. So for an example, I'll run this here. This preview, oh, I forgot to run the script. That's important. Okay, great. And then I'll run this. And what preview does is it looks at the first item in the data store, and you'll see it's returning 2 things. One is this 15-layer image that I talked about. That's our input. And then it's the single-layer output image. That's our above-ground biomass. And then we can preview what this data looks like. So these bright ones up here, that's from satellite 1. And then we have our 11 bands from satellite 2. And then it fills in this black one just so that it can be a nice little square. And then this is what our output looks like. Again, since the above ground biomass isn't necessarily between 0 and 1, I use the rescale function just so that we can visualize it in a grayscale kind of image. Awesome. Now it's time to start creating our model. We know that our input is going to be an image, and we know that our output is going to be an image. So we'll be creating an image-to-image regression network. And I love using the Deep Network Designer app to create my networks. Personally, when I'm working on deep learning workflows, I like to have a starting point, whether that's like a reference model that's already been trained or just an existing architecture. I like to have somewhere to start. That's totally preference. But there's a couple places that you can find starting models. You'll see I use this UNet layers, which is actually something that is available in our documentation. So I'll show you real quick. So semantic segmentation is something we talked about earlier. It's an image-to-image workflow, except it's image-to-image classification. And it's pretty easy to change a classification network to a regression network. I'll show you that in just a moment. So I was like, okay, let's start with a semantic segmentation network. And so I go to the documentation, I scroll down, I see design a network, and then we have all of these layers and existing network architectures that we can pull from. So I started with UNet layers.
Makes sense. Looks like we also have a question in the chat. So before we move on too far, we have a question that's asking on line 11 in your live script, you split the data set with ratio 0.95 and 0.025.
Yes.
And if you could give a little more info as to why that was the decision that you made there.
Absolutely, yeah. So I did that for both the input data store and the output data store. So I chose to make the numbers the same. That's important because we're combining them. But in terms of the actual choices of those ratios, the training data set that we have is a subset of the data set that's actually being used in the competition. So I wanted to make sure that I used a lot of my data for training. And so that's why I picked the 95% of my data for training. A lot of times you might want to pick something a little lower, like 80%. That's a little more standard, but you can play around with the numbers. And then for validation and test, again, I just kind of played around with the numbers, and this one seemed to work pretty well. And yeah, so this is something that you can change when you're making your own models.
Yeah, I think a huge part of any workflow like this is kind of just playing around, trying out different values, trying out different parameters, things like that. So you can definitely play around with those numbers. But yeah, that's what worked for us.
Great question. Thank you. Keep them coming. Okay, so I showed you where I got my UNet layers idea from, but also when you open the Deep Network Designer app, which is another one of our handy UIs, we have some pre-trained networks that are available to you. So you can scroll through and just see some of the pre-trained networks that are available to use, and then you can just retrain those using transfer learning for your application. But since I created my UNet layers, I'm going to import that from the workspace. And that's going to load into Deep Network Designer, which will allow us to visualize our network. So here you go. This kind of network is an autoencoder and decoder. So what that means is here you can see like kind of compresses the image and then decompresses the image. So that's what this like move to the right and then move to the left is. You can see the general pattern. And as I mentioned, it's currently a classification network, which we don't really want to be doing. So we'll take away this classification layer, we'll take away the softmax layer because that's used for classification. We'll go into our final convolution layer and we're going to change the number of filters to 1 because if we have one filter, that means that our output image will only have one layer, which is exactly what we're looking for. And then the layers over here are separated by type essentially. So I'm going to go down to output because I know I want regression. And we can just drag it onto our workspace and connect it. And there you go. It's all done. And you just hit export. And by default, it exports as lgraph1.
So easy. The apps are really cool. I think being able to
know.
Just look at everything and visualize it that way is awesome.
I'm a very visual person.
Yeah.
All right. And the last choice you have to make is what you want your training preferences to be. Unfortunately, this is a lot of little choices, and I played around with this for a while, and these were the choices that worked out best for me. And here you can see the validation data store. We use that during our training to kind of prevent overfitting, so that'll compare the performance of the model on the training data to the validation data and just make sure that it's not overfitting to the training data. And there are lots of options that you can set in your training options. Some of them are here, but if you want to learn more about the options you can set during training, there will be a link posted in the chat, and you can find this information in our deep learning documentation as well. Awesome. And then this is normally the part where you train the model. I included the function here so that you can see what it would look like, but this takes at least a few hours, and I didn't think we'd all want to sit here for that long. So I trained this ahead of time. I trained this network using these exact options and this exact network architecture. So I'm just going to load this network that I had saved. And then I'm going to evaluate the model on our test data to see how it does. So first we have to make some predictions. Again, this might take a little bit. I like to make sure that I'm being respectful of everyone's time. So I will load some predictions that I made ahead of time. And now it's time to see how our network did. So I'll do some visualizations. This first one doesn't tell us a lot. We see some general contours, some similarities, but then I remembered, hello, the above ground biomass is not between 0 and 1. We're measuring tons here. So again, I rescale the images, and now we can see more accurately what those measurements look like if we're visualizing them. And so this one on the left is the ground truth. It's the real answer, and the one on the right is what our network predicted. You can see that the one on the right is a little bit lighter, so it's probably predicting values a little higher, but in general we're getting the right shapes and contours, so it seems like the network is learning the patterns pretty well.
Yeah, definitely the two images are recognizable, which is awesome. It's
Yeah.
a good sign. We also have another question in the chat, so before we move forward, someone is asking, can I save my work with Deep Network App Designer and load it later? So let's go back into the app and see if we can do that.
Yeah, well, let's see, shall we? Okay, so this is the, let's zoom out. Let's see. Okay. So when you close the app, it does clear the network. So it does not seem to save it, but you can export code that creates this network architecture. And so that will allow you to kind of recreate all the work that you did. And when you save, okay, so like I exported my UNet layers, 1. So here, let's close this real quick. Going down a brief detour. So we can open the Deep Network Designer. Actually, you know what, let me show you the fun way to do it. So we have this Apps tab, and you can open Deep Network Designer from the Apps tab or from the command line. And so when you export your model, it saves all the work that you did. It saves, you know, all the changes that we made. And then you can just open that model again in the Deep Network Designer. So when we go to open it, it'll give us the option to import from Workspace or from Workspace. And we can select that LGraph 1 again. And that'll basically let us pick up where we left off.
Yeah, it's a little different from the image labeler app where there's literally a button that says Save Session. But yeah, if you export to Workspace or generate the code that's behind this, you can always just load it back in and work with it again. So
hope that answers your question.
Yeah.
Cool. All right. So we have a network. Seems to be doing pretty good on our testing data. Another way to evaluate it is with some numeric performance metrics. I chose the root mean square error, or RMSE, which can be portrayed by this function here. Essentially, it finds the difference between your predicted and your actual results, and then squares it, and then finds the average of the sum. This is considered one of the standard evaluation metrics of deep learning or machine learning models. So we have a built-in MATLAB function, RMSE, where you just pass in your reference or your expected output, your predicted output, and then we say all because we're working with a matrix here. Essentially, you know, it's two-dimensional, so we want to predict along all dimensions. And so we'll run that, and we'll see that the root mean square error is 33. That might sound a little high or a little low depending on what kind of application you're working on, but in this scenario where we're making about 65,000 predictions because it's on a pixel basis, it's not too shabby, if I may say so myself. And then the most important process of every deep learning workflow is iterate. I said many times that there are a lot of simple decisions that I made because this is our first model. And so, you know, try out different things, try out different architectures, change the way that you import your data. Maybe you only want to work with some of the satellite imagery or certain bands of the satellite imagery, and change your training options. There are so many decisions that you make when you are creating and training a deep learning model, so play around with it. Once you have a network you're happy with, you can predict on new data. So we don't know the output this time, and we'll want to export the results. So again, I pick a random patch of land, a random chip ID from our test data. I read all of the input satellite imagery the same way that we did when we were training the model. And then I will display that. So here, let's see what that looks like. All right, and so we've got this montage. This is, again, we've got our 4 bands from satellite 1, 11 bands from satellite 2, looking great. And now we can make predictions. So we'll use our input image. We'll run our new input image through the network. We'll show what the prediction is, and then we can export that image, that prediction, as a TIFF file, because that's how all of our images currently are. All right. And then we'll run this. All right, and so this is our predicted above ground biomass. We're going to take the chip ID and add AGBM to the end of the file name, and we'll export it as a TIFF file. And if you go into the current folder, we can see that that was added right here. And that is our deep learning workflow. We have done it, guys.
Yeah, very cool to kind of see it all beginning to end. So just to do a quick little recap, the first part was mostly, pre-processing images for these types of workflows. Most of the time, you're not just going to have a set of images you can feed directly into a network and learn from. You got to do some labeling or some augmentation or something like that. And so we showed kind of a few ways that you can do that. And then this full workflow of how after you do that, you can actually, train a model, make predictions, and you saw how accurate that model was. So yeah, very cool stuff. I see we're also getting a question in the chat. So the question is, have you performed hyperparameter optimization? And what GPU have you used in training the model?
I'm happy to take this one.
Yeah.
So I personally, I just played around with the hyperparameters. We do have an experiment manager that lets you play around with the training parameters a lot. And in terms of GPUs, I did not use a GPU to train this model. I know it helps speed it up a lot, but most NVIDIA GPUs are supported if you are looking to use a GPU to train your own deep learning models.
Yeah, and if you're looking at what types of things are supported, our documentation has lists of those things, so you can definitely quick Google search or search in the MathWorks documentation site should let you see a list of what types of things are supported. And yeah, like Grace said, we have UIs for a lot of different things. You saw how many apps there are when she clicked the little drop down. So definitely, the UIs just make it a little easier to visualize and interact with the workflow that you're doing. And we have UIs for lots of different stuff, including hyperparameter optimization.
Hope that answered your question.
Yeah. It looks like there are no more questions in the chat, so we can wrap it up. Thank you so much for joining. We hope that you learned a lot from us today. If you're interested in learning more, if you found this interesting, our documentation has lots of resources and examples that you can work through to, kind of go through this type of workflow yourself and see how it goes. We also have blog posts and other live streams and things like that. So lots of ways you can learn more about our products and what you can do with them.
And if you want to see the code that I used, but more in depth with a written explanation, the starter code that we have linked on the screen right now is the exact code that I used in our demo today. So if you have some questions or want to look into it deeper, check out that link.
Yeah. Yeah, with that being said, thank you for joining us, and thank you for engaging, asking questions. Hope you got a lot out of it.
And I hope you decide to participate in the competition.
Yes, definitely.
Cool. Thank you.
Thanks.